Hello everyone. So today I'm going to give a talk about Airflow and Lyft. So this talk is based on one of my previous engineering blog posts. So I put the slide as a go link here as well as a blog. So a bit introduction about myself. I'm an engineer at Lyft Data Platform. I'm a Airflow PMC at Computer. At Lyft, I'm working on different data products. I'm mostly ETL platform based on Airflow and a data product and metadata engines called Amundsen. So I'm going to talk about the data product Amundsen in the next week's Data Eng Conf. So first of all, how many people have been used Airflow or heard of Airflow here? Okay. So because this talk is will be very tight with the internals with Airflow. So this is today's agendas. So first I'm going to talk a little bit about Airflow in general, the community, and then talk about how we run or operate Airflow at Lyft, and then cover some of the upstream work that we have done at Lyft, and then summary. So Airflow in general. So Airflow is a very popular workflow management project created by Maxim, sitting here. So he just this project just graduated from the Apache incubator and become the top level project solution. We have about 20 PMC and committer, and we have seen many new active contributors in the community. So we have the project has been adopted by many companies, and we have many active contributors. So since last year, we have done the community have done many releases like 0.10, 0.10.1, 0.10.2, and today just shipped the 1.10.3. There are many notable new features. And the detail, could check out the link like in the Airflow GitHub repo. So like one of like Airflow RBAC as well as Kubernetes integrations. And the community recently just launched a new process for proposing architecture change called Airflow Improvement Proposal, or AIP. Currently there are about 20 plus proposals. And we have one of the PMC in the community also conduct a very useful Airflow survey. Please check out the link and see what the pain point, what's the use case for most of the users. So let's talk a bit about the Airflow and Lyft. Before diving into that, let me brief recap about the high-level architecture at Lyft. So at Lyft, like there are two sources of raw events. One is typical come from the Lyft mobile clients. One could be come from the API server. They will send event to Kinesis stream or Kafka. So currently we are in the process of moving from Kinesis to Kafka. And then we have a streaming ingest framework which will assist the data from Kinesis or Kafka into S3. And then we have user or engineer building derived model based on this raw events and persist in a Parquet format and store in Hive, or building even some Presto view or replicate into the Druid for faster access. We have many dashboard tools like Mo, Apache Superset, and Tableau. And Airflow is very critical in the piece because like a lot of derived table is built written in some Airflow DAG and managed scheduled by the framework Airflow framework. So this is the typical architecture for Airflow and Lyft. So we have like the UI, so which is a web server for user interactions. So user use the web server UI to kind of, for example, view the DAG, view the tasks, seeing the landing time, etc. So you talk to the Airflow meta store, so which store all the metadata like the DAG runs, the task instance, etc. And there's also an Airflow scheduler, which is a multi-process parser, which parse the DAG back, create task instance which are ready to schedule and send to an executor. And there's an executor framework which will schedule the tasks. So there's many ready or executor framework. We use Celery, but there's also Kubernetes executor as well as local executor. So one piece is pretty unique to Lyft is that we have a production instance box called task, which is used for fast prototyping and backfill purposes. So So here is our config Lyft. So our main cluster is still based on Airflow 1.8.2 versions. We cherry picked numerous in-house Lyft patches. So our scale. So the Airflow salary workers, we have 3 sets of ASG. The first ASG is we have 15. First of all are in AWS. So we have the first ASG is we have 15 worker nodes in R5 voice large type, which is a 16 vCPU and 128 gig memory. It's used for processing low priority memory intensive tasks. The second set of ASG is 3 workers, but it's a more is used for M4 voice large. It's a M4 voice large type. It's used dedicated to only those stacks that will have a very strict SLA, which mostly is a power the executive dashboards. The third set of ASG is one node, but it's a very big box. It's an M4 10x large, 40 CPU and 160 gig memory. It's used for compute intensive workload for critical teams back. Lastly, the backfill box is also a very brief box, M4 16x large, 64 vCPU and 256 gig memory. It's used for backfill. Here are some daily statistics for Airflow and Lyft. We have 600 DAGs in daily running, 800 plus DAG runs, and 25K plus task instances. And Lyft, a lot of DAG actually have hundreds of task instances. So let's go into how we monitor Airflow and Lyft. So at Lyft, we have building a very centralized Grafana dashboard for monitoring. Because Airflow is very important and power a lot of critical tier 1 or tier 0 data pipeline. The first most important one is what we call the Airflow availability. So there's 2 statistics here. One is about the scheduler or worker availability. The other is the UI availability. Scheduler and worker availability is we're using a DAG or building a DAG called Canary Monitoring, which is run like minutes, fixed schedule, and then publish certain statistic into StatD. And we are considering if there's no task that's been scheduled for 10 minutes, so the schedule worker is done. So there's a page immediately with trigger and send to our on-call. The second one is the UI availability. At Lyft, we deploy the web server in Envoy. So we leverage the Envoy membership help check to see if the web server is still up and down. The third one didn't show it here is there's an uptime percentage. So we consider Airflow is down, either it's a scheduler worker or web server is down in this case. Next statistic is called what you call a scheduler delay. It's also published by the Canary Monitoring DAG. It's mostly roughly equal to the task instance start time minus the task instance execution date. So for Airflow, the scheduler is impacted by a couple of components. For example, how fast the scheduler pulling or passing the DAG back, creating task instance, and how fast the salary workers pick up the task from the broker and schedule. So this statistic has to serve 2 main purposes. First is sometimes we want to tune and reduce the scheduler delay, and we want to see once we change the tunable configuration, what's the impact of the scheduler delay. Second is serve as alarming purposes. For example, if the scheduler delay has been shoot up very high, there's also a page we trigger for our on-call for further investigation. Second statistic is what we call the DAG last runtime. So it's measure the time that has been elapsed since the DAG file was last processed. So this statistic is if goes up, means that the scheduler sometimes has issues processing the DAG back. For example, it may due to some parser thread is occupied by the malicious DAG files. So and usually on call we'll also take a look in the scheduler log and see what's happening. The third one statistic is what we call the executor parallelism. So parallelism is a global config defined in the Airflow CFG to control the number of concurrent running tasks on the executor. So in this diagram, there are three lines The yellow line is showing the opening slots, meaning that, for example, if we define that parallelism to be 200 and there are running tasks about 20, opening slot is 180 in this case. The blue line is showing the number of running tasks at this moment. The orange line, which is showing here, if you see, is showing the number of queuing tasks, meaning it's waiting for scheduling. It could happen if even there's opening slot, and there still could happen like queuing tasks, because like some of the tasks could contain for very poor resource, which certain pool doesn't have opening slot. So normally we suggest you increase the parallelism if possible, but also please make sure to monitor your workers' no CPU utilization before you increase to a very large value. You don't want to max out your worker no CPU utilization. So here are showing some of the statistics. I think we contribute most of them back to the open source, but not sure if in the 0.3 version or at least in the master branch. So one statistic didn't mention in previously is called pool starving task. So it's showing each of the pool how many tasks is waiting for schedule. It's good to check if for user. It's good to check if your pool for your DAG actually is waiting contention for a certain pool. So now let me talk a bit about some of the customization we've done at Lyft. First one is what we call the UI auditing. So at Lyft, we sometimes hear from user asking why my DAG has been paused, who marked my task is a success or fail. So we built this feature basically to check what all the UI actions happening. For example, at this picture is showing someone actually turn off a certain DAG at this time. So it's leverage the existing FO log table and the flash signals feature to build that. The second one is what we call the extra link for task instance panel. So at Lyft, we want to customize certain task instance based on the operator type. In this case, for example, some of the task log is very difficult to read. It's either too long or too many text. We want to view the log actually in the Kibana and do some filtering. So you provide the Kibana log tab here. The other one is what we the announcement. So basically, we want to show this is the table URL. We want to show which task instance actually generated that table or created that table. The third one is what we call the DAG dependency graph. So at Lyft, we use mostly the external task sensor as well as the high partition sensor. We want to create a DAG dependency graph that basically showing different DAGs inter-DAG lineage. And it's created by an intern as a summer project last year. And using the Apple plugin feature, you could search the DAG and then only filter as showing the DAG lineage only for that certain DAG. The backend is powered by a DAG running at daily. So improve Apple performance a bit. So as mentioned before, some of the DAGs, actually many DAGs at Lyft have hundreds of task instances. And the default DAG runs is 25. So oftentimes we hear users saying, why my UI didn't run, my retrieval is fell too low, and why am I encounter timeout? So although it's good to kind of root cause and optimize JavaScript, so as a short workaround, then we change this one, change the display default DAG run number to the configurable, and we make it as file and Lyft. We never encounter the timeout issue again. A couple of tunable that impact the task execution parallelism. So the first one is what we mentioned before, parallelism. So it's a global config, but when you do backfill at Lyft, you also impact the backfill as well, because at Lyft when we do backfill we use a local executor. It controls the total number of task instances you could run. The second one is called concurrency. It's showing how much the number of total concurrent tasks could run by this DAG. The third one is called the max active runs. It's showing the how many active DAG runs you could have. So it impacts the backfill. So when you do backfill, you want to run multiple DAG runs simultaneously. So you suggested to increase this number when you do the backfill. The fourth will be the pool. Pool is more like resource isolation techniques at Lyft, at Apple. So you may also want to check if your pool is highly contentious. So some of the things we have done to improve the reliability. First is like we don't want anyone to arbitrarily increase the pool or create a new pool or increase the pool count. So we do source control for pool. So at Lyft, all the Airflow pool are defined in a source control GitHub file. It's configured and loaded in runtime. And on call, actually, we review the pool PR to make sure that no one is abusing this. And we build a set of integration tests to enforce some best practice and improve reliability. For example, we want to make sure all the DAG actually loadable within time threshold, have valid pool associated, and like external task sensor is valid, and the pool is used is not like an empty pool, and the sensor has some reasonable timeout, not like 1 day, not like 2 days or 1 week, and each DAG has a static start date and not a dynamic start date. Production debug. So at Lyft, on our team is a very document driven. So every time we have a production issue investigation, we always like document the investigation approach in the doc. And some of the basic methodology we have is like whenever a page is happening, so we will first view the centralized dashboard, seeing whether it's a UI or backend issue. Then go to either web server log or the scheduler log, and depends on the issue. Even if the log got rotated out, we will even check the log in Kibana or even S3. And then using different tool for further investigation. If the exception is thrown, we need to first understand like which part of the code is trigger this thing. Or if it is CPU or memory alarm, like using some of the system monitoring to like top to identify which DAG causing the issue. If the failure is related to Celery, so normally we will use a Celery Flower UI, which is a monitoring tool provided by Celery for further investigation. Some of the gotchas that we have encountered. So DST, so all our Lyft, all the executive dashboard is in has an SLA in PST, while the Airflow is scheduled in UTC. Although in upstream there's a time zone support, like in our internal version we haven't adopted that. And also in the upstream, the UI doesn't have time zone support yet, so there is a discrepancy here. The second is a DAG with dynamic starting. So if the DAG have a dynamic start date, it's sometimes very hard to predict when the DAG is scheduled. And long-running external task sensor. So we have seen at Lyft is many external task sensor have with long-running and sometimes doesn't even have valid external tasks. It could happen if the upstream DAG remove the task or rename the task, but the downstream DAG is not aware of this change, are still waiting for it. And this kind of external task sensors would occupy the slot, task slotted pool, is wasting resource. The next is we use a lot of high partition sensor, but high partition sensor doesn't work for partial partition, meaning like if sometimes the DAG want to wait for the whole table for that partition or that DS finish loaded before kickoff. It doesn't work in this way. And the backfill experience. At Lyft, we use a local executor to backfill. And we have seen like the backfill is, for example, like 2 verbals, 2 many logs, and sometimes the DAG run is not the status of DAG run is not created correctly. And sometimes we have seen like user got confused which argument is a DAG level argument or which is a task level argument. We have seen many times they mismatch these two. And lastly is like we at Lyft like 2 years ago, like before we adopt Airflow, not that many people use know how to write a DAG. But so we built a legacy high abstraction framework at that time. It's easy to, for user to use, but it's very hard to debug. So we are trying very hard to move away from this framework and encourage user to write the native Airflow DAG. Now talk a bit about some of the upstream work which may be benefit for others. So improve the backfill experience. So first of all, is that there's two, we provide two new options. The first is called reset _ DAG runs. So when Airflow when you use Airflow to backfill, if there's certain for certain day range, if that some day range has a successful DAG runs, Airflow will skip those skip backfill for those DAG runs. But sometimes you still want to do the backfill for those DAG runs because for example, you change the business logic, you want to rebuild the whole data set for that day range. With this one, you just need to by providing this option, Airflow will ask whether you want to clear the whole DAG run within that day range. And second one is we run _ failed task. So when Airflow try to do backfill, if there's any failed task, it will fail. So normally the approach is you need to run the Airflow clear first before run the backfill. With this option, you don't need to run the clear again. You just need to provide this option, and then Airflow will prompt the user to ask whether you want to clear the existing failed task. The second is we recently made a contribution to the upstream. So backfill traditionally doesn't respect the pool, meaning like even all your DAG or task is bound to a certain pool, it will still schedule as many as possible. So it's also benefit to do the resource isolations. So the next what we call is support the batch backfill. So we want the user to write the HQL, or some of the user write the HQL is in schedule run, you only create data set for one day. But when you do the batch, when you do the backfill, you want the HQL to run for a set of day range. So for that, we introduce a new macro called periods _ ds. Periods _ ds equals to ds minus schedule interval. And when user do the backfill, you could just change the schedule interval in the DAG file during backfill. Another one is a -c option in the backfill. So for example, in this case, you want to when you do the backfill, you want to override which high cluster you want to backfill. So next is DAG level access. So at Lyft, DAG level access is always having a real need. For example, there's some HR data, financial data that user or data engineer doesn't want the user to see. So the previous workaround is still build some isolated dedicated cluster for this use case. And Airflow since 1.10 introduced the RBAC feature. So it leverages some functionality from the new Flask framework called Flask App Builder. It should provide static role like admin, user, of reviewer, and public. It's good, but it's not enough. So because except the public role, all the other 4 roles could still see all the DAGs. So we implement this DAG level access feature, which provide additional granular access control on DAG level. So before going to Lyft use case, so let me talk a bit about the Fab script model. So there's a user table. So for example, each user is associated with multiple rows. And then for each view menu, could associate with multiple partition and create a partition view. And then the role could associate with those permission view. So in this case, for DAG level access implementation, each DAG will consider a view menu and has 2 permissions associated. So each role could actually just only see or access the DAG that is associated. So 1.10.2 include the initial implementation, and the 0.10.3 includes some of the enhancement. So as mentioned, there are 2 permissions associated. One is for read, one is for write. And user could use either the CLI or the UI to create a DAG level route. And once the role is created, you only could see the DAG that is viewable by that role. And user could declare the permission in the DAG file as well in this case, for example, is that this stack called DB2 ACL test. It declared the access control and only allow like the DB2's member to read and write. So at Lyft, we recently built a new cluster based on this master branch and on board a couple of new sensitive data use case to try it out. Each use case has its own ripple. Each row relationship or source control in a YAML file. So some of the right-hand side diagram show the user registration flow. Whenever the new user is logged in, Apple will check whether it's registered or not. If not, first need to register and update the underneath AB user table. And then user will see if he could able to see the row or not. If not, he will try to create a new row or use the existing row, which update the declared YAML file here. And once the YAML file has been deployed and all the row has been created and assigned, he could able to see the row belong to him. Some of the gotcha here, like new use, so this feature is still very alpha or beta stage. So the new user onboarding still needs a lot of make it more smoothly. Second is the integration between the Fab or the Flask App Builder framework and Google Authentication is not work very well and need a lot of documentation to get you working. The third is at Lyft, we have our internal ACL service from security. So we still trying to figure out how to integrate this deck level access with the internal ACL service. Some of the next step here. So I support this feature in beta internally and integrate with the internal ACL service for that level feature. Migrating, this is more like moonshot, like migrating all the existing deck to this new cluster. And lastly is explore running Apple with Kubernetes executors. So summary. So I think the community has been growing a lot, and today we share some of the experience operating Apple and Lyft, and share some of the upstream work, like how we improve the Apple backfill and how we do support the deck level access. And lastly, some acknowledgement is here a list of members who help to maintain Apple and Lyft. And special thanks to my Maxi here, who used to be a Lyft employee, that provide numerous suggestions for us. So, questions?
Thank you, Tao. Great talk. Gave a lot of details for people using Airflow. Any questions?
I just wonder, have you done any like HA work for your Airflow scheduler? Like, is there any need for that at all?
Sorry, could you repeat?
Have you done any like high availability work, like to make the Airflow scheduler more like multi-instance and stuff like that?
Not yet.
And do you actually see any need for that or not really?
So at scheduler, so far we haven't encountered this kind of issue, so we haven't planned for that actually.
I just wanted to ask about you said the backfill. You spin a local executor, so you have a celery executor running normally.
Yes.
So can you talk a little bit about how you manage running the two executors simultaneously?
Sure. So the backfill is running on a task, which I mentioned in the one of the slides. 1 second. So we don't use the celery executor for backfill. We use a local executor in backfill, meaning like every user just spin up their Airflow schedule using the local executor in this box for backfilling. So we don't use the normal celery executor for backfill.
But you're still looking at the same meta store, or?
So that's the thing is, so we have our own meta store connected to this backfill or task box. But if you want to still connect to the production Airflow meta store, there's still a way to allow you to do that. But we normally encourage you to just using the backfill specific meta store for backfilling.
And you mentioned you have a few dedicated clusters for Airflow workers. Do you have I'm wondering, how do you deploy Airflows? Do you have a master Airflow that can distribute the workflow to different clusters, or you have, say, one Airflow instance per cluster?
Oh, no, this is just one cluster here. So
Okay.
we only have one main cluster power the statistic. But some of the use case, for example, some of the DAG, that is very critical. We build like a very small dedicated cluster for them, but that's like, if for main cluster like the 600 DAG, this use case all happen in the one single DAG, one single cluster with a set of workers, set of the salary workers.
Okay, and it's deployed in one region of the cloud.
Any other questions?
First of all, great talk. So I had a question about like how you manage dependencies. Do you like? I assume with your hundreds of DAGs, you might have some DAGs that like basically two DAGs that depend on two different versions of Python libraries. How do you manage that?
Okay, so we didn't solve this one. So mostly is we have a single set of dependency for all the machines. So in this case, you won't say some depend on certain version and the other need to. There's only same set of dependency in this case.
Okay, last questions. Have any? No? Oh, yeah.
So you call out parallelism and concurrency differently. What are the differences?
So parallelism is a global config defined in the FOCFG, which control the executor total concurrency. And then the concurrency is only a DAG level config, only control your specific DAG, how many pass instances could be running concurrently.
One is a global, one's a per DAG.
All right. Thanks, Tao.